Okay, thank you. So I want first to thank the organizer who offered me the challenging opportunity to give the last talk today, talking about our work on a gastropod, so the abalone Haliotis species. But first, why work on this gastropod? So the Haliotis genus comprises more than 70 species worldwide, living in temperate, tropical, and cold waters. It includes also 50 species of commercial interest for aquaculture. In addition, its shell has a large variety of shape, color, microstructure, and composition. Here, I will focus on Haliotis tuberculata, which is a widespread nacreous gastropod living in marine rocky areas along the northeast Atlantic coast and in the Mediterranean Sea. Again, so this Haliotis tuberculata has a high economical and ecological value, and its nacre is used for jewelry. So if we have a closer look at its shell, so it's almost entirely made of calcium carbonate, aragonite, but for 1 to 5% of organic matrix. The holes you can see here are respiratory apertures. The shell is made of two main layers, an external one and an inner one, and I will come back on this later. If you turn back the shell, you will find the animal with its mantle here. This is a tissue that is covering the animal's body and that is responsible for the shell formation. You may know this part you are testing with your knife on oysters to know if they are still living before eating them. So now let's have a closer look at this portion close to the shell edge where the shell secretion occurs. So here is a schematic view showing you the mantle, the extrapallial space, that is a space between the mantle and the shell. The outer epithelium here, in close contact with the shell, controls the biomineralization process by producing and secreting organic matrix molecules and the other elements for the shell formation. As you can see, there are already some studies on the microstructure, the mineralogy, and the composition over the shell development of the abalone. Nevertheless, the role of the mantle cells in the precipitation of a given microstructure still remains to be clarified. In this context, we decided to investigate the geochemical composition of the shell and try to relate the trace element composition to the shell microstructure. We first worked on magnesium and strontium because these elements might be used as elemental tracers. So let's have a closer look at the shell growth and microstructure. So the abalone shell is slightly coiled with the first spire here and the growing edge there. So the shell growth is a step-by-step process, and the shell is growing up by successive addition of layers here and here, like an onion, for example. So we worked on the last centimeter of growth of the shell, which were cut like that. And so here is a section of this last centimeter of growth under an optical microscope with the stars representing the last deposited layer. So you can clearly see here the two layers I already talked about earlier, the inner one here and the outer one, sorry. And in fact, these both layers are secreted by the mantle, and they have a distinct microstructure that can be evidenced using scanning electron microscope. So the inner layer here, covering almost all the inside of the shell, so in contact with the animal, is made of nacre. That is highly ordered small plates. We already heard about this morning. This will be our N layer. The outer layer now has a spherolytic microstructure that consists in irregularly packed granules, and this will be our S layer. So our first point here was to know if these two microstructures secreted by the mantle of the abalone have the same geochemical composition. To do that, we use laser ablation ICP-MS technique that allowed to obtain trace elements at a given point. We analyzed 8 shells and obtained more than 100 data per layer. And so the answer is no. The spherolytic layer is significantly enriched in magnesium and strontium compared to the nacre layer. So to go one step further, we wanted to know if these elements are homogeneously distributed along a layer deposited at a single moment that we will call an isochronous line. But what is this? So here again, this is the section of the last centimeter of growth. And in fact, both layers at a given moment are deposited simultaneously. Here, with the black line representing the spherolytic layer and the gray one, the nacre layer. Okay, so the previous one will be there, for example, time -1, -3, and the next one will be there. And because each isochronous line represents one moment of deposition, and thus potentially one environmental condition, one physiological condition, the composition should be homogeneous, at least layer per layer. So for example, here, for the magnesium content in the spherolytic layer should be homogeneous, even if it is higher on average than what we observed in the nacre layer. Okay, so to see if this is exact, again, we did laser ablation analysis, but this time following one isochronous line. So here is what we did. What you can see here, again the same section, here are the craters that are left by the laser ablation procedure. Each crater has a diameter of around 40 micrometers. You can see that the craters are aligned along the isochronous line. We did 3 lines, one close to the last deposited layer and 2 others going back in time. We did that to know if the elemental distribution is the same, whatever the position in the shell. Because the shell composition can change between line 1 and line 3, for example, because of the environmental conditions that are not exactly the same, and because the shell composition can vary from shell to shell, from individual to individual, here is the way we will present the results. So here an example on line 2. So first, the point we obtain in the nacre will always be to the left of the diagram and highlighted in gray. Second, each analyzed shell will have a specific symbol. Here I will present the result obtained on 3 individuals of 2 years old. And lastly, again, because one moment should represent one composition, the diagram should more or less look like that. For example, in the spherolytic layer, we should have a constant elemental content, and the same thing in the nacre. even if on average the contents are different. So here are the results. So we have line 1 in blue here, line 2 in green, and line 3 in violet, with magnesium and strontium, and the different symbols for different shells. So first, we find again that on average, the magnesium and strontium content are higher in the spherolytic layer than in the nacre layer. Second, our assumption of a homogeneous distribution layer per layer is false, at least for the spherolytic layer. Indeed, in most cases, the magnesium, the elemental content is decreasing in the spherolytic layer when going towards the nacre layer, this last one being more homogeneous. And lastly, we observed differences in the magnesium distribution depending on the location of the line. For example, on line 1, the magnesium is increasing towards the nacre. In line 2, it has a U-shaped form, and in line 3, it is decreasing. So of course, these tendencies need to be confirmed, but I already observed such variation in elemental distribution in another mollusk, a cockle from Peru and Chile. So here, in this starting work that aims in the future to link the mantle activity to the shell composition, we observe that the Aliotis, with its mantle, secrete aragonite with 2 microstructural arrangements, and each microstructure has, on average, a different composition. So the question how? Is this average difference related purely to the microstructure? For example, does the magnesium enter more easily in the granules from the spherolytic layer than in the plates from the nacre, even if both are aragonite? Or is this difference related to differences in organic matrix content in both layers, this organic matrix being enriched in magnesium? Or at last, is this difference related to difference in mantle activity that would, for example, favor the passage of magnesium and strontium in the area that is responsible for the spherolytic layer deposition? In addition to this average difference, we observe a difference in the magnesium distribution along the spherolytic layer. So again, is this related to the microstructure, which can slightly change even in the same layer, as it has been shown by Schoene et al. In another mollusk? Or are these differences related to slight organic matrix content changes along a line as a consequence of mantle activity changes? Indeed, it has been shown that part of the mantle areas here, close to the shell edge, present some heterogeneities that may be related to the deposition of a given layer. Immunolabeling techniques allowed identifying specific matrix protein in the outer epithelium of the mantle of Aliotis here. More recently, molecular works allow identifying specific biomineralizing genes from the Aliotis tuberculata mantle. It has been, the expression of the lystrin A has been evidenced in the epithelial cell of the mantle in specific part of where the nacre is formed. So this confirms that lystrin A has a role in the formation of nacre. Nevertheless, the differentiation of mantle areas and their respective role in the formation of a given microstructure still remains to be clarified. So in our future work, we wished to investigate the interface between the mantle and the shell combining ultrastructural and geochemical techniques. So the mantle and the shell of the same individual will be studied in terms of ultrastructure and composition, trying to link the trace element distribution to mantle cell processes responsible for the formation of specific layers. Okay, so that's it. So I would like to thank my collaborators, the Muséum National d'Histoire Naturelle for financial support. Thank you for your attention, and if you have questions.